So we're going to start again. I have a YouTube here, and I'm going to use this YouTube as an electrolytic cell. What I'm going to do is I'm just going to put some potassium iodide in this. This is 0.1 molar potassium iodide. And then I'm going to use some inert electrodes. In this case, these are the low budget inert electrodes. This is just graphite. Here. This is another graphite electrode here. So I just have potassium iodide aqueous, 2 graphite electrodes there connected here. So what I want to do is I want to have the electrons flow from right to left. So I have the power supply here. Actually, this is not going to be long enough. So which one should I connect? The red is the positive. So should I put the positive over here or over here? On the right? No, I want it to flow from your right. Okay, I want it to flow right to left. Your right. And so the electrons are going to flow from here into the power supply and then out here. So this is correct. We want it to do this way. The other diagram is backwards. Okay, then what I'm going to do is I'm going to add a drop of phenolphthalein in here, just to see if there's any hydroxide that's present. It takes some time to diffuse, so maybe I'll put some more here. Just okay. Here we go. All right, then I'm just going to turn on the power. I'm going to crank up the voltage here. And then let's see what happens. All right, well, that's going. Let's take a look at what we have here. So I have a power supply here, and I connected the red to a graphite electrode here. Graphite. Graphite has got a very low oxidation potential, very high oxidation potential, very low reduction potential, very low or very high reduction potential. What is it? Low oxidation potential. Graphite has low oxidation, so we're not going to worry about graphite. We have potassium ions in here and iodide ions. This one phenolphthalein, not much. And so what's going to be oxidized here? And so this is the cathode of the power supply. And now this is going to be the anode, because the anode is where oxidation occurs. And so over here, am I going to oxidize the potassium ions or the iodide ions? The iodide. I'm going to oxidize the iodide. 2 iodides will form iodine plus 2 electrons. The potassium ions would have to strip an electron out of the core. And so potassium ion oxidation potential is negligible. We also have water in here, I forgot. But when it comes to oxidizing iodide versus water, iodide should be much easier to oxidize. It's a big ion. It should be fairly easy. Okay, now we're going to reduce something over here. We're going to reduce the species with the highest reduction potential. So what has the highest reduction potential? Over here. Water. Water has the highest reduction potential. In fact, we're going to take 2 waters and we're going to form 2 hydroxides. right? We need electrons here, 2 electrons. Two hydroxides, and we're going to have some leftover hydrogen. This leftover will be hydrogen gas. And so H is +1. Now it's going to go to 0. And so we should form at this electrode, we should form hydroxide, which we can detect using phenolphthalein. You see hydroxides being produced over here, the pink color, and hydrogen gas. That's harder for you to see, but I see it. There are lots of bubbles coming off the electrode. Those bubbles of hydrogen gas. And so over at the right-hand electrode, we should be forming iodine. Iodine's purple, but when it's diluted, it looks brown. Do you see all the brown solution in here? As it becomes more and more concentrated, it'll become more and more purple. So here we're forming iodine and hydrogen gas. And so this is electrolysis here using our power supply here. Well, we could do the stoichiometry with this. Because one of the things that the power supply measures is the current. The current here is 0.03 amps right now, or 30 milliamps. And so I could figure out how much of this I'm going to produce by using stoichiometry. And the stoichiometry is, this is a stoichiometric conversion factor. Because I have 2 moles of electrons, and for every mole of electrons, I'm going to have 96,485 coulombs worth of charge. It's a Faraday. And coulombs of charge is related to current. Because current is measured in amps. And 1 amp, or ampere, is defined as 1 coulomb of charge passing by in a second. And so I can use some dimensional analysis to figure this out. Although they use an equation here, I'm not going to use the equation. How long has this been running for? A minute? All right, so let's say in 60 seconds, I want to figure out how many grams of iodine I've produced over there. And so if I run this for 60 seconds, then I'm running it at a current of 0.03 amps. 0.030 amps is 0.030 coulombs per second. And then I know the Faraday constant is 96,485 coulombs per mole of electrons. And then I look at iodine. I have, for every 1 mole of iodine that forms, I have 2 moles of electrons that are consumed. And then I need the molar mass of iodine. So we get that over here. It's going to be 120, I'll just round it, 127 times 2, 264. And so this is going to be 264 grams per mole. And so in that 1 minute of operation, I can calculate how many grams of iodine I just produced. Likewise, I can just do the same for hydrogen. I can figure out how many grams of hydrogen I produced because the mole ratio is going to be the same, 1 mole of hydrogen per 2 moles, but the molar mass is going to be different. It's going to be 2.02 grams per mole. And so we could do stoichiometry. It doesn't have to be an electrolytic cell. This has quantitative aspects of electrolysis. We could, if we measure the current in a regular battery, we could figure out how many grams of reaction have occurred. And so stoichiometry with electrochem is easy as long as we know the definition of the amp and we know the Faraday. Now, Petrucci has this equation. But this equation is not difficult. This equation figures out how many moles of electrons. So the moles of electrons is up to this point. And so the moles of electron, according to Petrucci's equation, is equal to the current. Well, here's the current, 0.030 amps, times the time. Well, here's the time, 60 seconds. Divided by the Faraday. Well, here's the Faraday, 96,485. And so we could use this equation, but this equation is not necessary. We could just do dimensional analysis from way back chapter 1. We don't need this equation, and I don't even bother memorizing this equation because you could figure it out using units. All right, this is pretty much the last part of chapter 20, and so we're going to end there for that. We're going to start the lab, though, next. And so what we're going to do is we're going to work in groups.